time taken to complete the first revolution. He is bringing some condition. I'll highlight it. Just do think over on this one. Acceleration at any time t. It is not at. It's a at sim. It's not a symbol for a tangential. Okay, no. So what is initial initial velocity of particle? It is v naught. It is given for us. Look at the data given for us. Normal acceleration equal to tangential acceleration at any time t. So there's a data. Then initial velocity at t equals 0 is v naught and r is the radius. How to find the time taken to complete first revolution. If it's a uniform velocity motion, if it's a uniform circular motion, I think it's very easy. If it's accelerated motion, then we should use equations of. If it's a variable accelerated motion, we should go for integration. Are you getting no? There are three ideas are there. Uniform circular motion, quite very easy. Time taken 2 pi r by constant speed v naught. If uniform angular accelerated motion, we use equations of motion. If variable angular accelerated motion, we use integration. So first what you have to do, we have to identify what this condition is here. What is the condition given for us? Sir, but he has not said what type of motion. I think with the help of that condition given, we should identify what is the type of motion. There are only three possibilities, sir. Uniform circular motion, non-uniform, uniform angular accelerated motion, non-uniform angular accelerated motion. I'll start with this, A normal. I don't know anything, I'll just stick on to basic definition. What is A normal? Whatever be the thing, what is A normal? V square by R, tangential speed square of that by R. And what is A tangential? A tangential is what? So I'll go for omega square. And what is A tangential? Is equal to R alpha. Further, omega square R d omega by dt. These are the basic definitions, no? AT earlier in the derivation part, first yesterday I brought A theta. A theta or AT, both are same. Don't get confused here. Because there if I write T no, you start thinking it's a time, tangential. Now when it came numerical, no, I just preferred this particular prefix, T. So this particular symbol T, that one, both are same. Don't get confused. Okay, there's a definition. A tangential equal to R alpha. Sir, any motion is anywhere, whenever circular motion, just do remember this one. Or sir, I'll write also like this. What's wrong? Nothing wrong. Nothing wrong. Both are correct. So you can prefer either one. Since it's circular motion, no, will be very clear about what angular displacement, all that particular thing. That's why I'm preferring omega than linear speed. This is one basic application, because as we go for application, no, so you can see that expressing in terms of omega will be more advantage than the linear speed. After this, so it can also be like this, no problem. So here dt, that r get cancelled, so this will be d omega by omega square. So dt equal to omega to the power of minus 2 d omega. Let's go for limit. At t equal to 0, what was the initial velocity? Omega naught. Do we know that? As we can calculate, at any instant of time, let it be omega. So t is equal to omega I'm writing in detail so that you can understand things easily. What is omega naught? So we can write B naught equal to R omega naught, no? Because V naught is given. So this will be T minus 1 by omega. So let me go for limit here. T equal to, this will be 1 minus 1 by omega plus omega naught. So 1 by omega equal to, so what is omega? Omega equal to omega naught by 1 minus omega naught t. But what was the thing? Something is asking time taken to complete first revolution. What do you mean by one revolution, first revolution? How much angular displacement it will have? 2 pi radian. So something theta should be brought, no? We have omega. So omega, what I can write it as? D theta by dt. I'll take it out this. Now, if you want, I'll write it this one. You could have thought like this also. I'll put it here. Nothing wrong. You can do it by this method also. Now d theta, this will be little bit integration will trouble you. Omega naught dt. Now before that, what is the quotient of t omega naught? Minus omega naught. So this, what I do is, I'll adjust. Okay, now I think we can easily integrate it so that d of the quotient of t should be made equal in both denominator as well as numerator, no? Yeah. So this omega naught, I took help of this one. So further, this should be equal to the limit. Anybody limit should be 0 to t. This should be 0 to theta. So, but what was the question asked? Time taken to complete first revolution. So in one revolution, how much of angular displacement? 2 pi radian. So this will be theta. What should be the limit for this? Dx 1 by x. I'll write it in the corner. D of ax 1 minus ax. So what should be the limit? Log of 1 minus ax. Can you remember this? This is the basic formula. So here everything should be minus of log of 1 minus omega naught t. Substitute the limit 0 to t. This will be 2 pi log of, let me substitute upper limit 1 minus omega naught t minus log of 1 minus 0. 2 pi equal to, so this should be log of 0. So let me send that negative sign. I just displaying the total problem. This is 2 pi, no? So the further simplification of this will be minus 2 pi equal to log of, this log I'll send on to this side. This will become exponential. So what is the value of t now? So this T will be equal to, I'll write it here. T should equal to 1 by omega naught 1 minus e to power of minus 2 pi. What is omega naught? V naught by R, because omega naught is not given, no? Okay, this is the answer. So just see, like you have to stick on to the basics, nothing big. You have to just analyze properly what is the situation given for us. I'll display complete question, so just make observation. Yeah. So now look at this. These are the very important part. What are the conditions here? What is AN? AN equal to what? Omega square R. What about A tangential? A tangential equal to what? R alpha. But sir, they are equal. This is what you stick on to circular motion. A normal. V square by R, V omega, omega square R.
Sir, it's R by V naught, sir.
Yes, sir.
R by V naught. I'll to change here. Yeah. R by V naught. Yeah. So what are the conditions that arise in the circuit? What are the conditions that arise in the numerical? The basic definitions will remain same. A tangential dV by dt, or R alpha, alpha equal to what? D omega by dt. These are the things which will be taking help here. So you do get plenty of questions now. Just a math based. Shall I conclude like this? It's just a math based. The basic formulas, and if you know the integration, I think you can manage. This will going to help you a lot when you go for rotational kinematics. Then once again, I'm going to come back here. Because see, when we enter into rotational mechanics, it's all about the rotation. A student must have a basic idea. What do you mean by tangential acceleration? What do you mean by normal acceleration? What do you mean by centimeter? Tangential velocity, angular displacement, number of revolutions. I think you'll be in a far better position as you proceed further. Where all you see circular motion, there's a background. If you have, there'll be enough. See, just like kinematics, what we did is linear kinematics. This is what now is a circular kinematics or curvilinear kinematics. So how the kinematics you learned there, it is helping you. Now similarly, towards any curved path, this background is essential. This is a basic. I'm not telling this application. It's a purely basic. So how skilled you are here. So this is going to help you a lot in coming chapters. So I request you to work out many numericals. See, until let's see, now we know definitions. A normal equal to omega square, but the same thing as number of numericals came, the things were totally different, no? So as you work out more numericals, it'll become very easy for you. Oh, in this situation, I should think like this. In this situation, I should think like this. This particular methodology will come for you. So once you get that confidence now, finish or you can manage application part very easily. Okay, fine. So you get plenty of numericals to work out. Either you take icon or Cengage book. No, plenty of numericals are there. You can manage. So solve as many as possible and try to think. So in every problem, what all you should ask yourself: tangential velocity, angular velocity, tangential acceleration, normal acceleration, angular displacement, distance covered, then number of revolutions per second, and also the average quantities. Everything, whether he will ask or not, leave it, but you prefer that, you go for that.